In this fifth module, we are discussing the internal structure of hadrons and strong interactions. In this fifth video, we will examine the consequences of the fact that strong interactions become stronger with distance. After having watched this video, you will understand why one cannot observe free quarks and what happens when a quark-antiquark pair is created in vacuum. Because of the enormous amount of energy stored in a color field at large distances, separated color charges will create additional particles instead of becoming free quarks or gluons. A dynamic separation occurs, for example, in the E plus E minus annihilation into quark-antiquark pairs at high energy, far above threshold. The left figure shows the Feynman diagram, the right figure the kinematics in the center of mass frame. The central figure is an example of an event of this kind showing multiple hadrons in the final state. Again, there are two approaches to qualitatively understand the process of hadron formation in the final state, a chromostatic one and a more chromodynamic approach. In a chromostatic approach, the quark-antiquark pair creates further quark-antiquark pairs as soon as the original pair is separated by of the order of 1 Fermi. At this distance, the stored field energy is large enough to do this. This process continues until the relative momentum of the quarks is sufficiently moderated to permit the formation of bound states. Hadron formation occurs along strings, a kind of elastic band connecting two color charges, thus with limited transverse momenta. The hadrons thus form jets, which approximately follow the initial direction of the quark and the antiquark. In a more chromodynamic approach, the process can be visualized in terms of a quark-gluon cascade. It starts with the emission of a gluon by the quark or the antiquark as shown in this Feynman graph. This gluon can produce either a quark-antiquark pair or a pair of gluons according to the elementary vertices of QCD. Because there are more gluons than quarks, splitting into gluons is more probable and is thus shown in this Feynman graph. The strong coupling will become the larger, the more the invariant mass q squared of the virtual particles involved diminishes. At the end of the cascade, the quarks will form colorless bound states. It is clear that this approach cannot be used up to the end of the hadronization process. At small q squared, the coupling constant becomes so large that a perturbative expansion in powers of the coupling constant will no longer converge. In this domain, collective effects take over, which end up by the formation of mesons and baryons. They must be described by more phenomenological models. The hadrons are formed in vacuo at the end of the quark-gluon cascade. Their transverse momenta with respect to the original quark direction are thus limited by Heisenberg's principle to some 300 MeV. Hadrons are thus concentrated around the initial quark direction and form jets. Their transverse momentum is small and independent of the quark momentum. Thus, jets become more and more collimated as the quark energy increases. If the first gluon emitted in the cascade has sufficient transverse momentum with respect to the natural width of a jet, a third hadron jet will become visible along the gluon direction. One thus observes an event with 3 jets as shown in this example. These events can be attributed to the reaction E plus E minus goes to QQ bar gluon. The cross-section for this process, E plus E minus goes to QQ bar gluon, is calculated using the Feynman diagrams shown on the left. The gluon emission from a quark has all the characteristics of a Bremsstrahlung process. Its amplitude has 2 divergences, becomes very large for the emission of a low-energy gluon, which is an infrared divergence. It also blows up for a very forward emission by a collinear divergence. In both cases, the quark and gluon jets will merge. 2 as well as 3 jet events are counted among the hadronic final states. In the calculation, we must thus add their cross-section to obtain the total hadronic cross-section we introduced in video 4.5. One thus obtains a better approximation for the ratio R at high energies in better agreement with the experimental data as shown on the right of this graph. Jets appear without exception whenever a high-energy quark or gluon converts into hadrons. This means, first of all, that the probability for the hadronization process is 1. It is an inevitable process. Second, the conservation of energy momentum and the limitation of transverse momentum by Heisenberg's principle means that jets follow the direction and represent the energy of the initial quark or gluon, and this with a more and more narrow collimation as the energy increases. This event shows a final state with two energetic jets produced in a proton-proton collision at the LHC. On the top, you see a zoom of the inner detector and the calorimeters. On the left, you see multiple vertices. The high luminosity of the collider causes multiple reactions at the same bunch crossing. The two reactions with most of the deposited energy, which are colored in red and green, show back-to-back jets, which are strongly collimated. The bottom image on the right shows a histogram of the directional distribution of energy. The two narrow peaks correspond to the direction and the energy of the two jets. This concludes our short discussion of strong interactions. In the next module, we will deal with weak interactions and the Higgs mechanism.